This conference will now be recorded.
Hello everyone. This problem is related to chemical properties of carboxylic acid. Some methods we have already seen and some methods we will also discuss in today's class, and after that there will be some problems. This problem is related to coal-based electrolysis. What is coal-based electrolysis? That is the last reaction we discussed in the last class. So in this case, a molecule is given and it is undergoing electrolysis. Water is present. What will be the final product that we have to find? Options are 2-butene, that is double bond present, 1-butane, this is also sorry, not double bond but triple bond. Then option C is also triple bond, and option D is saying that it is both B and C. So first we will see what is in general what is coal-based electrolysis. So this is coal-based electrolysis where we take sodium or potassium salt of carboxylic acid and it must be 2 molecules. In presence of water, final products we are getting, this is the main product, alkane. So 2 R group that are present in sodium salt of carboxylic acid, 2 R groups now connected together and we are getting alkane, and NaOH, H2CO2, these are the byproducts. Now as I have said, 2 CO2H group. Now this 2 CO2H group in sodium or potassium salt form, it may be that they are part of the same molecule. So as you can see, the molecule that is given in the question where 2CO2K, which is potassium salt of carboxylic acid, that is present in the same molecule. So you don't have to take 2 molecules of it, right? Now if that is the case, when it is normal RCO2Na, 2 R groups connected together and you get the product, right? But if it is in the same compound, then what will happen? Obviously these 2 parts will be removed. Fine. So as if these 2 parts are removed and there will be a new bond formation. See, if I am writing RCO2Na like this, RCOONA, and I am also writing the molecule that is given in the question. So it is RCO2K, CO2K, and 2 methyl group both sides. So when it is general structure I have written, this is first molecule, this is second molecule. In this case, what is happening? These 2 are now connected by a newly generated bond, and this part is removed. Okay. Now if these 2 parts are present in the same molecule, so intermolecular reaction will happen, and there is already a CC double bond, but a new bond will be formed. These 2 parts will be removed. So basically what we will get? We will get a triple bond. And here you can see these 2 radicals, because in the last class I have discussed the mechanism. You can also check that mechanism. So it goes through some carboxylate radical. So that is why here radical picture you can see. But final product is these 4 carbon and triple bond. And what is the position of triple bond? It is 1, 2, 3, 4. That means position of triple bond, it is 2. So it will be obviously it is not alkene, it is alkyne, but it is 2-butyl, not 1. So correct option here will be this one. Which of the following compounds will undergo decarboxylation on heating? We know when it is beta keto acid like this. Beta keto acid. This is beta keto acid, because with respect to CO2H group, this is alpha position, this is beta position. So at beta position there is keto group, so that is why we can call it beta keto acid. So we have to check which compound out of these 4 is beta keto acid. The first one, it is obviously not beta keto acid because there is no acid group. It is 1,3-diketo compound. This is 1 position, then 2, then 3. 1,3-diketo carbonyl compounds. Then come to 2. This is actually beta keto A star, because this is A star group. With respect to A star group, this is alpha, this is beta. Now decarboxylation for beta keto ester is possible. First you are hydrolyzing it and you are converting it towards acid, that is, if you are converting it to acid like this, CO2H, which is nothing but this molecule, that is a third molecule. Under that condition, if you are heating it, then decarboxylation possible. But first you have to hydrolyze this ester to beta keto acid. From beta keto ester to beta keto acid, then only simple heating you can get decarboxylation product. But it is in ester form, and in the question, if you read carefully, it is saying that only it is undergoing decarb, so only on heating. We are not using any hydrolysis condition, acidic or basic. So that is why this will not give. Though there is a possibility to give, but we are simply heating it. We are not doing any hydrolysis. So that is why 2 will not give. Then 3, it will give because this is actually beta keto acid. And if you consider 4, if I write the structure of 4 elaborately, CO2H, then COOH. Now we have 2 CO2H group, right? And you can consider the carbonyl group as the keto. So this is alpha position, this is beta position, this is gamma position. So at gamma position you have some keto group, though it is the C double bond O which is coming from CO2H, but still it is not beta keto acid, it is gamma keto acid, right? So this will also not give decarboxylation. Only beta keto acid, which is compound 3, this will give correct, this is the correct answer, right? Option 3, that is the correct answer. So number 5 is decarboxylation by Hans-Digger reaction. In the previous class, different types of decarboxylation methods we have seen. The first one, which is very simple, it is simple heating. Just remember the last example, last problem that we have discussed, that is simple heating. Then you can use soda lime, you can use that is electrolysis. So now we have reached another decarboxylation method, which is known as Hans-Digger. This is a name reaction. In this case, what we do, we take silver salt of carboxylic acid, RCO2 minus Ag plus, in presence of X2 and CCl4. This is solvent. X2 means halogen. Now it may be bromine, it may be chlorine. And what product you are getting, that is a final product, you are getting Rx. So here alkyl halide is the final product. Okay. Alkyl halide is the final product. Then CO2 is liberated, and silver, its fate is now it is converted to AgX. So when you are using X2, 1X is attached with alkyl group, which is the alkyl group present in this salt, and another X is now attached with Ag. What is the mechanism of this reaction? Ag2O. How you can convert first this carboxylic acid to the silver salt? You can do it by using Ag2O, silver oxide. First you are making the actual starting material for Hans-Digger, which is not directly the carboxylic acid but silver salt of carboxylic acid. Then halogen we are using bromine. So this what is the reaction occurring here? Ag and Br together, it will be removed in the form of AgBr, and O-Br bond is formed. Now this bond, if there is homolysis, that means single electron, odd electron will be over oxygen and also over bromine. So this is not heterolysis, this is homolysis. After that, so that is why these arrows are single-headed arrow. There will be removal of carbon dioxide. So this part will be removed in the form of carbon dioxide, and now you are getting R dot. And Br dot is already present in the medium, so these two together it can make RBr. Now see here what is written. It is actually aryl bromide, but it may be any type of alkyl halide. In general, the term should be alkyl halide, as we have used in this case. Alkyl halide, this alkyl group may be 1 degree, 2 degree, 3 degree, primary, secondary, tertiary. There is no such problem. And it may be also that this R is some aromatic group, that is benzene ring. Then we will call it aryl halide or aryl bromide, particularly in this case. So this is the mechanism it is undergoing. That is, the mechanism is going through radical mechanism. Okay. The reaction has some disadvantage. What is the disadvantage? Because it requires the presence of pure dry silver salt. So the silver salt of carboxylic acid, which is the starting material for this reaction, that should be in very pure dry condition. Now, maintaining this condition practically, it may be there may be some problem. So for alternative, what we can do, you can also make, that is, excellent results are obtained if you are using excess of red colored mercuric oxide rather than silver salt. So now you are not taking any silver salt of carboxylic acid, rather you are using HgO, which is red mercuric oxide. Temperature 76, you have taken this carboxylic acid. Here we have taken cyclopropane carboxylic acid. Rest of the things, there is no such change. Bromine is still there, CCl4 is still there, and you are getting same type of product. See, alkyl halide. In this particular example, you will call this alkyl halide as cyclopropyl bromide. Fine, and these are the byproducts. So if you are not able to maintain this condition, which is pure dry silver salt, you can use this alternative. Problems regarding decarboxylation again. Which of the following beta keto carboxylic acid doesn't undergo decarboxylation? We know that when it is beta keto carboxylic acid, simple heating you can expect decarboxylation. But it is asking that among these three, one compound, it will not give decarboxylation. But there is another possibility, none of these. That means all these three will give decarboxylation. So we have to look at the structure very carefully. Beta keto acid, it undergoes decarboxylation because of this type of mechanism. So see, I am writing this acid in this way. So when we are heating it, what is happening? This double bond between carbon and oxygen is broken. It is taking this hydrogen. Oxygen hydrogen bond is broken. New C double bond is formed. Now this CC bond is broken and you are getting new CC bond. So what we are getting? We are getting OH CC double bond, and from this part we are getting carbon dioxide, which is removed. So that is why it is decarboxylation. And this is in enol form, but after all it will be converted to keto form, CH3COCH3. That is acetone. But the important thing here is that this type of mechanism that you are seeing, that is involving, see how many atoms? OHO, then CCC. So it is 6-member transition state and ring-like transition state. So this must be in planar form. But if the molecule is such where planarity cannot be maintained, then reaction will not be possible. Because for this type of 6-member transition state mechanism, planarity is very important fact. Now look at the options. Option 1, this is beta keto acid, because with respect to CO2H group, if this is alpha, this is obviously beta. But in this case, this carbon, it is sp3 habitus, it is tetrahedral. But remember, because of this type of bicyclic structure, planarity maintenance, this will be difficult. Because this CO2H is directly attached to this position. So that is why this will not give decarboxylation. But if you look at 2 and 3, no such problem is there. This is alpha, this is beta. So in this case, if I draw the mechanism, yes, it is possible. So what will happen? Rest of the part, there is actually no change. C double bond O, and in this side double bond O, O and H. So this 6-member transition state you can easily constant, there is no such problem. Okay, so in this way it is possible. Similarly, if you take this one here also, planarity maintenance, there will be no such problem. C double bond, okay, let me write it here. This is O, H, and we have here CH, CO, CH3. So this is also beta keto acid, because with respect to CO2H group, this is alpha position, this is beta position. So see how 6-member transition state is possible. There will be CC double. So in this way also, there is no such problem with planarity. So this will also give decarboxylation. Only the first one, this will not give decarboxylation, and that is why it is the correct option. Next question. This is related to Hans-Decker. For the Hans-Decker decarboxylation reaction, which of the following is false? Two statements are there and two equations are there. A, B statement, C and D, two equations. So one of these will not be correct. So let's see one by one. The first option is saying it involves reaction between silver salt of acid and bromine. Now this is true, right? Then it is used to prepare alkyl bromide. That is also true, because the final product is basically alkyl halide. So if you are using halogen bromine, obviously final product will be alkyl bromide. Now the third one is equation, RCH2CO2Ag. So this is silver salt of carboxylic acid. You are using bromine, fine. And what you are getting? You are getting RCH2Br. So in general, if you consider Hans-Decker equation, this alkyl part which is present in carboxylic acid, in the final product, this alkyl part is basically attached with the halogen atom. So this is actually true, right? That is, the general equation is you take RCO2Ag and after reaction you get Rx. So this R is RCH2 in our case, in option C. So that is why this is correct. But the last one is saying that RCO2 CO2Eg, same silver salt you have taken again, but now the final product written RCH3. But final product is not alkane. Final product is alkyl halide. So that is why this is false for Hans-Decker decarboxylation, and this is the correct option. Fine. Which dicarboxylic acid in presence of a dehydrating agent is least reactive to give anhydride? We know when we have any dicarboxylic acid, you are using some dehydrating agent, which means the agent which can accept water molecule. So one water molecule will be removed and you will be getting anhydride. So in general, if I write, suppose we have acid RCOOH. Another acid I am writing in this way, in reverse orientation. So when you are using dehydrating agent, H of one acid, H of another, it is removed. So there is formation of now RCOO, then again CO and R. Now in this case, I am showing you the reaction taking two individual carboxylic acid, but it may be part of the same molecule. If you look at the options, here the 2CO2H group, that is part of same molecule. Fine. Now in which case it will give anhydride, but it will be very low reactivity. So in which case, if you consider the first one, the anhydride structure that you will get, it will be like this. Benzene ring at ortho position to carboxylic acid, and after removal of water, this should be the structure. Now there is no such problem. We can see it is a generation of 5-membered. The new ring that is generated, that is 5-membered. If it is option 2, now the anhydride that you will get, it will be something like this. This is also 5-membered. So here H and which will be removed. If you are using 3, now see, when it is the second one, it is also 5-membered. This is also 5-membered. When it is 3, now what will be the ring, that is number, total number of atoms? So it will be 1 H and H is removed. So there will be one more oxygen here. So COC, and in this side you have total 4 atoms. So that means the structure will be like this. COO. So it is 7-membered. And if it is option 4, already there is a 5-membered ring. And I'm just neglecting this stereochemistry, that is not important. So in this case also it is 5. Only in case of option 3 it is 7. Next you have to consider stability of ring size. Now among 5 and 7, obviously 5 is more stable. Okay, if you consider starting from 3-member ring to 7, obviously 4 and 5 is the most stable. So that is why as you are getting 7-member, this is not very stable. So though it can give anhydride, but yield will be very low. So that is why this is the correct option. Next question. This is related to hydrolysis of ester. Ester, though it is not directly mentioned in the question, it is simply asking decreasing order of ease of alkaline hydrolysis. Oh, sorry, ester is mentioned. Then it's fine. So it is ester because you can see CO2 R group in all these molecules. Now, what is the common thing in all these 4 options? The common thing is it is aromatic ester. So if you just consider these groups which is at 4 position or para position with respect to CO2 ET, because all these groups are CO2 ET, that is same. Only the substituent and para position is changing. So for first you can consider as if it is hydrogen. For the second it is Cl, then NO2, then OCH3. Now what I will do, I will write in general the structure of ester. So it is RCO OR prime, right? And in this case you are using alkaline condition and hydrolysis. So what happens? Water will act as nucleophile and it will attack at this carbon. So this is the first step. I am not going into the detailed mechanism. Just remember, this type of attack obviously will occur. H2O will attack as nucleophile, and the C double bond O that is present in ester, that is actually the electrophilic part. So this carbon is electrophilic. Now if there is any substituent present in this left hand side part which can increase the electropositive character of C double bond O, obviously now this carbon will be more electropositive, that means it is more electron deficient. So water can easily attack because water is nucleophile. It will prefer more very electron deficient center. Higher is the deficiency, better will be, that is higher rate you can expect. Now look at the groups. Among these groups, NO2 is the most electron withdrawing. So if I write order, NO2 is most electron withdrawing. After that it is chlorine. So this is 3, this is 2. After chlorine, it is basically hydrogen, because OMe, though there is oxygen, but actually because of this type of lone pair, it has plus R effect. So in this, because of this, OMe is electron donating group. So this is 1 and this is 4. So maximum rate will be for NO2, minimum for OMe, and 3 at first position present in option 1 and 2. So these two cannot be correct. Okay, but after 3 there is 2 which is present in both options, but after 2 you have 4 in 1 but 1 in 2, but it is actually 1. So option 2 is the correct option. Okay, so this is the decreasing order of ease of alkaline hydrolysis. So the conclusion is when it is para-nitro substituted ester, that will give maximum rate. Fine. So this is why it is decreasing order. This is that is option 2 maximum, option 4 minimum. Remember, we have total 4 types, broad types. We have divided the chemical properties of carboxylic acid, A, B, C. All these 3 are done. Okay, so A, it is related to acidity. Then we have seen reactions regarding the OH group of carboxylic acid. Then you have seen in option, that is not option, sorry. You have seen the third category, which is reactions involving the full CO2H group, both C double bond O as well as OH. The fourth type is substitution reaction involving hydrocarbon part. So if this is RCO2H general carboxylic acid structure, this is the hydrocarbon part. So whatever reaction is occurring in this hydrocarbon part, that will be discussed under this heading. So the first reaction, which is in blue color, number 1, alpha halogenation. It has another name, Hell-Vollard-Jelinski reaction, but in short you can call it HVZ. H for Hell, Vollard, B Zielinski Z. Carboxylic acid, it is alpha, also called alpha halogenation. That means with respect to CO2H, just focus on the alpha carbon. This is alpha carbon and there is also alpha hydrogen. So if this hydrogen is replaced by halogen, that is actually this reaction. Carboxylic acid having a hydrogen are halogenated, that is alpha hydrogen. When I'm saying hydrogen, it is alpha hydrogen. On treatment with chlorine or bromine in the presence of small amount of, either you take red phosphorus or you can also take PbR3. Final product is alpha halocarboxylic acid. So with respect to CO2H group, this position is alpha and at alpha position you have halogen. So that is why the final compound you can call it alpha halocarboxylic acid. In this case it is alpha bromocarboxylic acid. Next example also see, here you have taken red phosphorus bromine, but you can also take PbR3. In this case also we have two alpha hydrogen. Remember, requirement is that there must be at least one alpha hydrogen, otherwise how you will get substitution of this hydrogen. So you are getting alpha bromo carboxylic acid. One question may arise that when you consider simple aldehyde molecules and ketone molecules, and if you are trying to do same type of reaction, that is from aldehyde and ketone, suppose there is some alpha hydrogen with respect to C double bond of carbonyl group and you are substituting it with halogen. So that type of reaction is also possible. But in those cases, you have not used this type of phosphorus compound. But why for carboxylic acid, we are using specially this type of extra reagent? Okay, why not we are using simple base? Because if you are using simple base, there should be generation of some carbanion at the alpha position by removal of alpha hydrogen. And then you can substitute this carbanion with bromine. But that is not possible. So this is the reason. If you want to do alpha halogenation of carboxylic acid, though it is having alpha hydrogen, but its reactions are not like ketone and aldehyde. So if it is simple ketone and aldehyde, suppose I am taking acetaldehyde, very simple. So these three are alpha hydrogen, CH3. Now when you are using some base, there will be negative charge, and I'm directly writing negative charge here. Suppose this is negative, this is CH2. So this negative charge, this type of resonance possible, and ultimately you are getting enolate basically. Okay, so you can get enols or enolates, but this type of enols or enolate formation is not possible when it is carboxylic acid. Now suppose you have taken CH3 COOH, so this is carboxylic acid. But if you are thinking why not same type of enol formation is possible here, because here these three alpha hydrogen and this single hydrogen of CO2H, if you consider acidity, obviously this hydrogen is having higher acidity than this three alpha hydrogen. So when you will be using base, this H will be removed, not the alpha hydrogen. So the problem is that carboxylic acids will be deprotonated before the removal of alpha protons. That is, this H will be removed, deprotonated, not alpha hydrogen. And if alpha hydrogens are not removed, it is not possible for you to get enols. So that is why here mechanism is completely different, and you cannot expect reaction that is going via formation of enols and enolates. Here the mechanism is different. Fine, you have to use some phosphorus, red phosphorus or PbR. Now we will see the mechanism. There are total 4 stages if you consider the mechanism. The first stage is conversion of carboxylic acid to acyl bromide. So this is the first step. And first step is occurring in presence of this phosphorus reagent. Actually, if you use red phosphorus and bromine combination rather than taking PbR3, then also this will be produced in the medium. So ultimately it is same. Here in the first step, OH is simply replaced by Br and you are getting acyl bromide. Next step is tautomerization of the acyl halide, or you can say acyl bromide, to its enol form. So this H, it will take part in enol formation. So now one of this H is here. This is enol. Number 3, third step, bromination of alpha carbon of the enol. See here what will happen if I write bromine in this way. So this OH bond will be broken, there will be C double bond O, and this double bond will take one of the bromine. So now you are getting CBr, fine. So this is the product of after third step, and you can say this is bromination of alpha carbon of the enol. Next, that is the final step. Number 4 is hydrolysis. So when you are doing hydrolysis, this Br is replaced by OH, and this is the final product, that is alpha halo carboxylic acid. So these are the 4 stages of the reactions mechanism. You can also draw more detailed mechanism, but this is the summary of the mechanism. There are actually 4 steps. Now in the final step, as you can see, we are using water. So rather than doing hydrolysis with water, so you are saying hydrolysis because you are using water. But suppose you are not using hydrolysis, rather if you are using alcohol, what will be the fate of this molecule? So same molecule, same type of molecule, see, like this. I am talking about this molecule. So alpha bromo acyl bromide. See, this is also same type of molecule. So instead of taking water, if you have taken methanol, that is any alcohol, not just methanol, then what is happening? This Br is now replaced by this methoxy group. So in general, if you take ROH, it will be COR, OR. So you are getting basically ester, alpha bromo ester, fine. And if you are using ammonia instead of water, now Br is replaced by NH2 and you are getting alpha bromo amide. So one important application you can consider for this SVZ reaction is that in this case, the previous product, that is just consider this molecule which is just the product before hydrolysis. This product you can, if you are using ammonia, rather than getting alpha halo carboxylic acid, you can produce alpha halo ester or alpha halo amide. So it is up to you which compound you actually want to produce. You can make different types of products: alpha halo carboxylic acid, alpha halo ester, alpha halo amide. And that depends on what you are using in the final step. If it is water, it is alpha halo carboxylic acid. If it is methanol, alpha halo ester. If it is ammonia, it is alpha halo amide. If we consider, sorry, this is number 1, alpha halogenation. Here it will be actually number 2. And number 2 is basically reaction which is occurring in the aromatic ring if the carboxylic acid is aromatic carboxylic acid. So this is number 2, where reaction is occurring in the ring itself, and the ring is benzene ring. So obviously you will take some aromatic carboxylic acid, and we know when it is aromatic compound, 2 types of reactions are there: electrophilic substitution or nucleophilic substitution. Now in this case, we will consider electrophilic substitution, and here the benzene ring itself will act as acid nucleophile, and the attacking reagent, that will be actually the electrophile. So any one of these hydrogen, suppose if you consider benzoic acid, ortho position hydrogen, meta position hydrogen, or para position hydrogen, any of this H will be replaced when it is electrophilic substitution of aromatic ring. And that depends on whether the group that is already present, in our case it is CO2H, whether this is electron withdrawing or donating. If it is donating, then ortho and para hydrogens are replaced by electrophile. If it is withdrawing, meta hydrogens are replaced by electrophile. So as we know, carboxylic group is deactivating, it is actually meta directing. So only this hydrogen will be replaced by the electrophile, and in this case the electrophile is basically Br+, which is generated from bromine. So finally what you are getting, meta-bromobenzoic acid or 3-bromobenzoic acid, right? So the first reaction is halogenation because halogen is introduced. Now the second reaction is, this is halogenation number 1. The second one is nitration, where you are using nitrating mixture of concentrated HNO3 H2SO4, and the electrophile in this case is NO2 plus. So NO2 is inserted in the meta position. And you can also do sulfonation reaction number 3. In this case, just use concentrated H2SO4. So this meta hydrogen is replaced by SO3H group. So 3 types of examples here you can see. But in this case, Friedel-Crafts reaction is not possible. That is benzoic acid or any derivative of benzoic acid, they do not undergo Friedel-Crafts reaction, as this CO2H group is so deactivating. What happens when you are trying to do Friedel-Crafts reaction? We know in Friedel-Crafts reaction we use Lewis acid AlCl3. Now Lewis acid means it is electron deficient, and what happens? This Lewis acid, it will be attached, that is bonded to the carboxylic group, because in carboxylic group you have OH and there is some lone pair over oxygen. So this will be having some interaction with AlCl3 and this will be attached. But we want AlCl3 to act as catalyst. But if it is already attached to by this undesired reaction, not reaction, that is complex formation type, this lone pair is donated to AlCl3 and it is already stuck there, but it cannot proceed further, where it should actually act as catalyst. Then only you can get Friedel-Crafts reaction. Fine. So that is why this is the problem. We cannot get Friedel-Crafts reaction, but you can get halogenation, nitration, and sulfonation. Sorry, this is the name. There is a mistake in animation. This is substitution in aromatic ring. So after finishing chemical properties of CO2H, now we have reducing action of formic acid. So chemical properties, when we have discussed, we have seen 4 broad categories, and under each broad category we have different types of reaction. But this slide, whatever you will see, this is also reaction of acid only, but this is exclusively for formic acid, because formic acid, if you look at the structure, it is quite different compared to the other carboxylic acid. Carboxylic acid in general, you can write the structure like this. But formic acid, which is the first member, this R group is basically H, and the next member is acetic acid, where instead of H, now you have some carbon. Fine. So this formic acid, in its structure, if you look carefully, it is very unique because it contains both aldehyde group as well as acid group. So obviously it is containing acid group because CO2H is present, but see, it is also having aldehyde, right? That means you can expect reaction from this acid, particularly formic acid I am talking about, which you expect from aldehyde molecules. Fine. So that is why, just like other aldehydes, formic acid also can give, it can show reducing property, just like other aldehydes. Fine. So, and itself it will get oxidized. So this is one example, which is basically Tollens reaction or Tollens test, which test is basically done to identify whether any aldehyde group is present or not. But formic acid will also give positive test because of presence of aldehyde part. So in Tollens reagent, which is ammoniacal AgNO3, main reagent is Ag plus because it is acting as oxidizing agent. It will accept electron from this reducing agent. In our case, it is formic acid, it is not aldehyde, and it will be reduced to silver 0, which is responsible for silver mirror. So test is positive. Then another example, Fehling test. Formic acid can reduce Fehling reagent also. Fehling solution which is in detail you can also check in the aldehyde part, where details of filling test is already discussed. I am not going into details in this particular portion. So in filling solution, what happens? It is originally blue colored because of presence of this ion. It is in alkaline medium, but finally after accepting electron, because this is the oxidizing agent, it will accept electron from formic acid, and ultimately now it is converted to copper plus. Cu2O, it is cuprous oxide, copper plus, and that is why red precipitate is formed. So there is some visual color change, and PPT formation is also there, which is the proof that the test is positive. So failing test, tolerance test, both will be positive by formic acid, and this is uniquely for formic acid only, exclusive, not for other carboxylic acid. Okay. Test for carboxylic acid group. That is, if you have any sample, you want to know whether there is any CO2H group present or not, these reactions you can do. Though these reactions already discussed, but separately I am talking under this heading, that what are the tests that you can do so that you can identify in unknown sample there is CO2H group present or not. So first of all, as it is very acidic in nature, the simple thing you can do, you can use some blue litmus, and if it is converted to red color, when you are touching it with aqueous solution, just put a drop of this aqueous solution. If it is changing its color, then it is positive test. Then carboxylic acid gives brisk effervescence because of the evolution of CO2, and it is very fast. Fine. So when you use sodium bicarbonate and you are having any sample of carboxylic acid, there will be liberation of CO2, and the source of this CO2 is basically bicarbonate ion, not CO2H, because the fate of this part is it will be converted to sodium salt. So this test also you can do where there is no such color change, but you can easily observe this brisk effervescence. Some bubbles will be coming out from the solution. Another thing you can do, you can form ester, because we know esters are having some fruity type of odor, any ester. So if you have any sample of RCO2H, you can use some alcohol, R prime OH I am writing, and acidic condition, H plus is the catalyst, and you will be getting RCOOR, which is ester formation. So after formation of this in the test tube, if you smell it, you will, if you are getting some specific odor which is characteristic odor of ester, then it is another evidence that unknown sample is containing RCO2H. Functional derivatives of carboxylic acid. In the first slide or second slide, I have already given you some idea about what is functional derivatives. Now again I am doing this because when you have RCOOH and you are having you are replacing this OH part with some other group, suppose ClNH2OR prime OOCR, it is actually OCOR. Don't think it is OO bond, it is OC double bond OR. So compounds such as acid chloride, that is when OH is replaced by Cl, it will be acid chloride. This is the general structure. Then amide, RCONH2, then ester, and this is anhydride. So these names are also given in the second column. So they are derivative of carboxylic acid, but see their properties are completely different from the carboxylic acid. Fine. They differ from carboxylic acid only in the nature of the group or atoms, that is replacing this OH. And depending on what groups you are using in place of OH, you will have different compound. Now reactivity for these four derivatives that you can see here, that is obviously not same. Now when I am saying reactivity, what I am trying to say, suppose you have carboxylic acid, you are using some nucleophile. So obviously this nucleophile, it will attack this carbon, right? But suppose if in this OH part you have some other group Z, in general I am saying, now this Z, whether it is donating or electron withdrawing, depending on that, electropositive character of carbon may change. If Z is highly electron withdrawing, electropositive character of carbonyl carbon will increase. As a result, nucleophile can easily attack, so reactivity is maximum. But if Z is very donating type of nature, suppose it is showing class R effects because of some lone pair, then the electropositive character of carbon will be highly reduced. Nucleophile will not try to attack, so reactivity will be less. So depending on what is the nature of Z, electron withdrawing or donating, depending on that, reactivity will change. So this is the relative reactivity of the derivatives. Maximum is acid chloride, then anhydride, ester, and then amide. But we will also see what are the actual reason behind it. So explanation for the reasons of reactivity. One explanation that you can give, that is based on basicity of the leaving group. So when it is weak base, we know it is a good leaving group. Now leaving group means what? It is completely detached from the original substrate. Now it can detach only when it is very stable itself, and stable means it is weak. If it is reactive, you will call it is unstable. So reactive means unstable and stable means it is weak. Okay, not reactive. Now look at these derivatives. Here the leaving groups are in blue color. This is leaving group. OCOR is the leaving group. For ester OR prime, for amide NH2. There is also example of carboxylic, but just focus on this 4. Here reactivity is increasing as you are moving towards upper side, right? And these are the leaving groups. Now they are very, if you consider their basicity, as you move from Cl minus to RCO2 minus to R prime O minus to NH2 minus, basicity is basically increasing. Fine. So see, amide is very good base. Then R prime O minus, that is alkoxide, it is good base. Now this is gradually the basicity is not so high. Now why this is not so high? You can see here this type of resonance is possible, and because of this type of resonance you are getting another equivalent structure. So this type of resonance is basically making this anion very stable. So as it is very stable, it is not so reactive. And Cl minus is stable because the negative charge is stable because of high electronegativity of chlorine. So that is why as you are moving down, reactivity is increasing, and if you are moving up, it is becoming less basic. So as this is very reactive base, obviously the corresponding compound amide, it will be least reactive, and this is the explanation. Another way also you can give the explanation. The stronger this electron donation from Z. So as I have mentioned, suppose this is the general structure RCOZ. Now you can write this C double bond O in this fashion, just after breaking one pi bond. But another way also you can draw the structure, that is if this lone pair over Z is taking part in reaction, now you'll be getting this type of combo. So see, in this case of 3, the double bond character of CO is reduced. The double bond is present only in structure 1, not in structure 2 or 3. Fine. So the stronger is electron donation from the group Z, the less positive, or you can say less is the double bond character of the carbonyl carbon. Less electrophilic, that means it is not so electropositive. And the order of electronegativity, or you can say the order of electron donation capacity, it is like this. So maximum order, that is maximum electron donation, is possible in case of amide because of presence of this lone pair over NH2. Okay. Now NH2, it is having least electronegativity, but if you consider from a donation point of view, it is having maximum donation because it is least negative electronegative. That is why it can donate maximum. After that, OR you can consider. Now compared to NH2, in case of OR, electronegativity is high because oxygen is more electronegative. Okay, so that is why though here Placer effect is possible, but it is lesser than NH2. Then we have OCOR. So when it is anhydride, now here also you can expect Placer effect, but what happens? Both sides there is carbonyl. So suppose you want to check the electropositive character of this particular carbonyl, but remember lone pair can also be shifted towards other side. So as a result, the chance that the lone pair is coming towards this side, that is becoming less. Fine. And in case of Cl, it is not as such. And also you can consider that the size of carbon and chlorine, they are not matching. They are not from same period. So the double bond between CCl is not very good. Fine. So this is the second explanation, which is resonance effect, based on which also you can explain why the reactivity order is, you have already seen in the previous slide. Here you can see it again. This is max, this is min. Okay. Now related to this compound, which is amide, here we will discuss acid amide, RCONH2, one reaction which is only for amide, and this reaction is very that is common reaction, Hoffmann bromamide degradation. Why we are calling it degradation? Because in this reaction, see, you have started from RCONH2, which is amide, 1 degree amide, and you are ending with 1 degree amine. So here this carbon is lost, so there is decrease in number of carbon, so that is why this reaction is called degradation. In this case, you use bromine and 4 potassium hydroxide, it may be NaOH also, just 4 HO minus is required. And byproducts are K2CO3, KBr, H2O, but actual product is RNH2. So remember, this is conversion of amide to 1 degree amine. Okay, let's discuss the mechanism first. So in this case, if you, that is detailed mechanism, I am not going here, but it is shown here. If you are interested, you can check it. And just remember, in mechanism, when you are seeing, just even if you can't remember the detail, at least try to remember what are the intermediates produced. So if this is a starting position, this is one intermediate which is N-bromamide, RCONHBr. Another intermediate is isocyanate. Fine. So this will be produced in the medium. Now why I am saying so? Suppose you can get some question where the starting material is not RCONH2 but it is N-bromamide. So in that case also you can get product. This is also Hoffmann bromamide. Fine. So that is why remembering the intermediates are important. And in this question you can see it is asking that the number of moles of NaOH and bromine that will be required per mole of amine. Different options are there. So from this balanced equation, you can see this is 1:1:4. So 4 moles of NaOH or KOH will be required and 1 mole of bromine when you have 1 mole of amide. Okay. Now this question, you can see that why remembering the intermediates are also important. It is asking which of the following will not give Hoffmann bromamide. We know Hoffmann bromamide is possible for this type of compound, but it is not limited to this only. If you have any derivative of like this is the derivative of this compound produced in the medium intermediate. If this is the starting material, then also it will work. So this is amide, so obviously it will give this reaction. This is PHCONHBr. Now it matches with this type of structure, which is not directly the starting material, but it is intermediate. So this will also give positive reaction. Then we have PHCONH2. This is also amide, benzamide. This will also give positive, but this one, it is not 1 degree amide. See, it is substituted. One H of NH2 group is substituted methyl. So this will not give Hoffmann bromamide. So this should be the correct option. In substituted amide, it will not undergo Hoffmann bromamide. Because if you are using this, then isocyanate formation not possible. See, isocyanate is Rn double bond C double bond O. This is, its formation is possible only when you have at least 2 hydrogen. Because the first hydrogen is removed in presence of HO, the second hydrogen is also removed in presence of HO. Then only you are getting this isocyanate. But if it is substituted, that is, you have some methyl alkyl group already attached to amide NH2, then it will not be positive. Hoffmann bromamide degradation for benzamide. Benzamide is PHCONH2. Gives product A. Upon heating with, that means now you are heating A with chloroform and NaOH and you are getting B. You have to find the structure of A and B. Now the first reaction is basically Hoffmann bromamide. So if it is PHCONH2, obviously the structure of A will be aniline PHNH2. So based on this, you can cancel this option because aniline is not present as A. But all these are aniline, right? Option 1, 2, 3. But what is B? When you take any primary amine and you treat it with chloroform NaOH, this is actually carbylamine reaction. And carbylamine reaction is identification test for 1-degree amine, where some foul smelling compound is produced, which is that is NC attached compound, which is responsible for this bad odor. And that is the indication that here primary amine is produced. So when you are treating A, which is aniline with CaCl2KOH, basically it is conversion in general. If I write carbylamine, conversion of RNH2 to RCN. In our case, R is benzene, so it will be PHCN like this. So this option is the correct option, right? And in this slide, we have explanation for the reasons. Sorry, it is not explanation for the reason. It is actually uses. Okay, it is uses. Manufacturing of soaps needs higher fatty acid. Uses of carboxylic acid. So just go through it. There is nothing much to discuss. For soap formation, we use higher fatty acid, long chain hydrocarbon. That is, this R part is long hydrocarbon chain. Then food industry also there is use of it. For example, acetic acid is used for making vinegar. Sodium salt of organic acid, that is benzene ring, will be present in our part. It has application in preservative formation. Then pharmaceutical industry, different drugs are produced. Acetic acid, it has so many applications. Then hexane dioic acid, which is dicarboxylic acid, it is used specifically for generation of this polymer. And methanoic acid is actually formic acid. And organic acids have huge application in making dye perfume. Remember, you can use it for formation of ester, and ester is having some specific sweet smell. So that is why for perfume formation it is used. So we are at the end of this session. Thank you for listening.